Thank you very much, and thank you for inviting me to talk here. And for those of you who came, spending your Valentine's Day evening here. So I will talk about the origin of black hole mergers seen by gravitational wave sources. So let me just first discuss the title. So I will try to argue that black hole mergers form at the centers of galaxies, and some of the galaxies, 1% of the galaxies, are so-called active galaxies. So these are the galaxies where the central supermassive black hole at the center of the galaxy is accreting gas actively. And so it shines with a very bright emission. So these, because as the gas is inspiraling in the direction of the black hole, it can still shine before it falls through the event horizon. And these are the most luminous objects actually on the sky that you can see. So these are the active galaxies. And I will argue that these black hole mergers happen in the vicinity of the supermassive black hole in these gas disks. But this is an open problem, as I will highlight. So this is now an extremely exciting time, because finally gravitational waves can be observed in the universe. So this is a completely new window on the universe, very different from all of the electromagnetic channels that existed in the past. And every time a new window opened up on the universe, very new things were found, which were unexpected at the time. So for example, when radio observations were made, it was the first time that supermassive black holes were discovered at the centers of galaxies. So there's this very bright radiation coming from the centers of galaxies. That's evidence for supermassive black holes. And similarly, when the microwave background, the microwave observations were made, the light of the Big Bang was discovered, which was an amazing discovery. In gamma rays, there are these very bright sources called gamma ray bursts, which are now believed to be neutron star mergers. Those were discovered, which was sort of unexpected. And now here's a new window, the gravitational wave sky. It is just being opened up at the moment. So in this talk, I will describe some of the recent discoveries made with gravitational waves and some of the interesting questions that came up and which are still unsolved. I will try to present some new ideas to explain these sources, but this is a completely open field. So, I should say that gravitational waves have already been awarded for the detection of gravitational waves, but not for the explanation of the sources. So this is a big open problem that is awaiting the solution. Okay, so I should just show you what we're talking about. So there are two black holes orbiting around each other. And these black holes, this should be a movie. Yeah, it works. Are orbiting around each other, and they are bending the light rays as they orbit. And this is by the background galaxy image is distorted by the black holes. As the black holes are orbiting, they lose energy because of gravitational wave emission. So, and so they start to spiral inwards, because as they lose energy, they approach each other, and eventually they coalesce. And so this was well known. This was predicted by even by Einstein at the time. So the gravitational waves were predicted for a long time, but they were not observed until very recently. And there are different types of instruments that can detect gravitational waves, and only one of them is available at the moment, but there's future for this field opening up a wide range of frequencies in gravitational waves. So at the moment, only the very high energy gravitational waves are observable. So high frequency gravitational waves, and these come from mergers of stellar mass black holes. In the future, there are plans for space instruments where three satellites orbit around the sun, trailing the Earth, and they do laser interferometry between them, and they can detect supermassive black hole mergers, so in this frequency range. And there are pulsar timing arrays. So these are basically radio detectors that are observing pulsars, so rotating neutron stars in the galaxy, and they are timing the arrival times of these pulses from different neutron stars across the galaxy. And so if gravitational waves pass through the system, so in this case, the pulsars and the Earth, they basically distort the arrival times of the pulses of the pulsars. And you can use this to observe supermassive black holes as they orbit around each other on tens of years of periods. So on very low frequencies, nanohertz gravitational wave frequencies. There are some ideas for, well, it's known roughly the sensitivity of the instrument, and there are ideas for the expected astrophysical background for these different types of frequencies. And so it is conceivable that these types of instruments will also measure gravitational waves soon, but it may take a while. So in this case, for pulsars, it will take until enough data has accumulated, which is expected to be around 2025. And for LISA, we have to wait for the instrument to be launched in space. And then hopefully it will measure supermassive black hole mergers immediately. But at the moment, there's already this exciting window now at between 10 hertz and 1,000 hertz. And this is done by these laser interferometries. So this is on Earth. There are 3 locations at the moment, actually 4 now, because there are 2 instruments in the United States, 1 in Italy and 1 in Japan. So that's CAGRA, which has joined the collaboration. And so these are, so in these instruments, light rays are passing through these laser beams through these tubes, these vacuum tubes. And as the gravitational waves pass through the instrument, it distorts the geometry of these tubes. And then there's an interference pattern that can be detected if there's a gravitational wave. So in this way, you can detect gravitational waves. And what you see when black holes merge is something like this. So you basically, you see this type of pattern as the instruments move. So basically the lengths of the arms of the instruments change in this way. And so for different types of mergers, this is what was seen. So there's an oscillation and the amplitude slowly increases and the frequency increases. And this is as expected because as you have two black holes orbiting around each other, as they lose energy, they orbit on smaller radius orbits. And in this case, they orbit faster because if you're closer to the sun, you orbit faster. For example, Venus and Mercury orbits much faster around the sun than the Earth. And so this is why the frequency increases and the amplitude increases because they are closer and so they emit more gravitational waves. And so there are different events. So all of these events take only a few, not even a second, so a few hundred milliseconds. And so now there are plenty of these mergers that have been observed. And so here's a summary of the existing observations. Here I'm showing the masses of the merging objects, and blue shows the gravitational wave observations. And there are also red points, which are electromagnetic observations. So it turns out you can detect stellar mass black holes also through electromagnetic emission, and not the mergers of stellar mass black holes, but if you just have a star orbiting around the stellar mass black hole, you can observe so the star can lose mass and this mass can be accreted by the black hole, and the black hole then shines in X-rays. And you can use this observation to infer the mass of the black hole. So the spectrum of the X-rays tells you what the mass of the black holes is. And this is what was measured. So it ranges between few solar masses. So this is in solar masses relative to the sun, and up to 20 solar masses. But the blue points are the gravitational wave observations. They show that so each of these little binaries are, when they merge, they produce a merger remnant. And this is, so in this case, a 23 solar mass black hole merged with let's say a 30 solar mass black hole, and it produced 50-something solar mass black hole remnant. And there are also these observations, which are electromagnetic. And these are believed to be neutron stars. But there are some gravitational wave observations now, up to 5, which may be neutron star mergers and neutron star black hole mergers. So this is what we see. And so you can use the gravitational wave data to infer the properties of the sources. So here, so this is coming from the collaboration paper. So the name of the instrument is LIGO in the United States and VIRGO in Italy. And they detect gravitational waves coincidentally. And so there's this collaboration. And from their publication, you can find what is for each of these mergers, you can find what was the masses of the 2 objects. But there are large error bars. So this is the error bar. So in this case, for example, this merger had masses between 40 and 80 solar masses. And this is the primary, and the secondary black hole, which was merging, had a little bit smaller mass. You can also detect the mass ratio shown here, but the errors are huge. And you can also detect the spin of the black holes, how fast the individual black holes were spinning. But so the error bars are again large, but you can already start to say something, as I will show you. And you can also detect the distance, how far is the source from the Earth. And so it's interesting how the mass is distributed for the black holes compared to the stars. And it turns out that the distribution is very top heavy, meaning that there are many more massive black holes, relatively more massive, like 40 solar mass black holes or 30 solar mass black holes, than stars in proportion, based on the observations. But of course, the more massive objects are easier to detect, so it's not that surprising to find many high mass objects. You can see them to a larger distance. But even the merger rate, so if you take that into account and predict what is the mass distribution of the black holes in the end, independently of the detection distance, even that seems to be top heavy. So heavy objects are more common among black holes than stars. And so here's another. So this is for the primary mass. The previous one was the chirp mass. It's a combination of the secondary mass and the primary mass. But so obviously more massive black holes are rarer, but for stars, this is an even steeper function. And so there seems to be a feature arising here, which is unexplained. And it will, in the future, if you have more detections, it will be clear if this is just a statistical, scatter, or if this is real. But what's interesting is that this mass distribution extends to very high masses, and it's currently not understood how these types of black holes may form from stars. They could be results of mergers between previous generations of black holes. And you can also measure the spins of the black holes. In particular, one component of the spins, which is a component perpendicular to the orbital plane of the merging binary. And this spin value that they detect ranges between -1 and +1 in theory, meaning that if it's +1, then the spin is maximum. So there's a rate at which the black holes can spin. And there's a maximum rate where the black holes are basically spinning at the speed of light, and they cannot spin faster than that. In that case, this is normalized to 1. And if it's 0, then they are not spinning. And if it's -1, then they are spinning, but spinning in the opposite direction as they orbit. And you can also have 0 spin in projection if they are spinning with a high spin, but the spin direction is perpendicular to the orbital motion. And what you can see is that the spin distribution is centered around 0, so a little bit offset. It's not clear if this is truly significant, but the point is that either the black holes are not spinning, or for some reason they are spinning exactly in the perpendicular direction to the orbit, which is an interesting, unexpected observation. And you can look for various correlations between the spins and the masses, for example. Are the spins higher for higher masses or something like this? But there doesn't seem to be any clear trend here. What you can also observe is the rate of mergers in the universe. And here's how this evolved. So first, when only 2 detections were made, the first 2, the rate of mergers was predicted to be between 200 and 600 per gigaparsec cube per year. So this is the density of mergers per unit time. And so obviously from 2 events, the error bars were large on this number. But as newer and newer detections came along, now here we are in this range. So it must be between 17 and 45 per gigaparsec cube per year. And I will show you that this is already surprising. So this is higher than expected generally from one of the astrophysical channels. And there's also a rate of neutron star coalescences, but there are only a few of these observations. And so the rates are now between 13 and 1900 per gigaparsec cube per year. And it's not clear why this number is so much higher than that number. The number of neutron stars in comparison to black holes should be around 3 times as much. So you might expect 3 times as more mergers among neutron stars than among black holes, but it seems like there could be much more. There are also mergers between black holes and neutron stars. And so you can start to eventually see the distance distribution of these mergers and see if there are more mergers at high distances when the universe was young, or vice versa. And there's a bright future for gravitational wave astronomy because you will see, so the detections show that the merger rate is 17 to 45 per gigaparsec cube per year. What this means is that there are 1 to 3 mergers per day within a distance of redshift of 0.5. So this is a way of measuring distance for astronomers. How much is the light redshifted because of the expansion of the universe? This is a relatively small distance in cosmological sense. So the largest redshift observed among electromagnetic observation, so AGN, so active galactic nuclei, is around 7 at the moment. So compared to that, 0.5 is a relatively small distance compared to the size of the universe. And even in that small region, there are 1 to 3 mergers per day, which will become accessible as the instruments are improved in the future. So there are plans for improvements, and you will reach redshifts of up to 100. So if those black holes existed at the time, you will just discover them, and if they merge. So this is really interesting. And so there are interesting questions that you can now ask. How did the black holes form and evolve? So you can now test these theories observationally. How did the black holes get so close? So this is a big question, because if you look at stars, so the stars are often observed in binaries. So they orbit, they are in binaries, not like the sun, but many of them, half of the stars are observed in binaries. And you could expect these stars to eventually, if they form into black holes, they could merge because of gravitational waves. But the problem is that the time it takes for them to merge is more than the lifetime of the universe, much more. It's like 10 to the 10 times more than the lifetime of the universe. So they should basically never merge just because of gravitational waves. They will only merge if you put them close, and then gravitational waves can drive them to merge. So the question is, how did the black holes get so close that they actually merge? And another question is if the masses, spins, and merger rates match the expectations. And I will show you that there are big problems with the theories. So first question, why are the black holes so massive? So this is what I was telling you about, that you have these massive stars around black holes, then the stars can lose mass and the black holes can accrete this mass and shine in bright X-ray radiation. You can use the spectrum to measure the mass of the black hole. And if you measure the mass, these are the electromagnetic observations, they tend to fall into the distribution is bimodal. So there are many of these systems with masses around 1 or 1.4 solar masses. These are believed to be neutron stars. And there are these objects which are believed to be black holes around 10 solar masses. But the LIGO sources, the gravitational wave sources, are much more massive. But why is that? Seems to be inconsistent. So I will now describe some of the theories that may explain the astrophysical origin of the mergers. So one is stellar evolution. This is what I alluded to just before. So you can have binaries, two stars, and the stars can grow. These are massive stars, and they become red giants at some point during their life, and they run out of hydrogen, and they can engulf the other star. So there can be a significant mass transfer between the two stars. And ultimately, the red giant turns into a black hole. There's a core collapse, supernova explosion. And then a black hole orbits around a star or the stellar core. And then the other object also turns into a black hole, and then ultimately they merge. And so here the nice thing about these stellar binaries is that there are many of them. So you might think that maybe there's some fraction of them are closed binaries, and maybe they can form these merging black holes. So interesting point is that massive stars are typically in binaries. So the massive stars, which form black holes and not white dwarfs and neutron stars, for example, happen to be in binaries much more commonly than low mass stars. And 25% of them are in triples. And in that case, you have a third object. The third object can help to merge the binaries. So it can produce a gravitational effect, which increases the eccentricity of this binary, such that you have a close approach, and then ultimately gravitational waves can drive the system to merge. So these are some of the ideas with stellar binary evolution explaining the sources. Another set of ideas is the dynamical environment. So here, the argument is that you have these very dense regions of the universe, dense in stars, typically globular clusters and galactic nuclei. So globular clusters are these dense islands of stars in the galaxy. So these systems, these clusters, orbit around the galaxy in the galactic halo, in the dark matter halo. And there are millions of stars in a few light year regions, so much smaller region than you would see stars in such numbers otherwise. And there are galactic nuclei. The centers of galaxies are very dense in stars. And mainly because of the supermassive black hole, it tends to collect all the stars with its big gravity. And so in these regions, the density, well, in globular clusters can be 10 to the 3 to 10 to the 5 times higher than the average density in the galaxy, the stellar density. And here, the density in galactic nuclei can be million to 10 billion times higher than in the galaxy. And so the question is it possible that these black holes just fly close to each other, so close that they will actually emit gravitational waves and merge? And for that process to happen, the close encounter process, you can calculate what is the probability of that. And it turns out it's proportional to the square of the number density. This is, for any scattering process, this is true. So obviously, higher density leads to a higher rate. But since the density in these environments is up to, let's say, 1 million times larger than in the galaxy, you can see that the encounter rate is even larger. So it's 10 to the 12 or 10 to the 20 times higher. So in these environments, it is possible that there are close encounters. And so then you can form binaries by close encounters. So you can have 3 objects come close, and there's a chaotic interaction between the 3 objects. One of the objects is ejected, and you are left with a binary, which doesn't, the 2 objects which are left over do not have enough energy to go back to infinity. And so they are by definition bound. So you form binaries by dynamical interactions in these dense systems. And once you have binaries, you have additional interactions which can shrink the binary, and ultimately you get to such a close separation that gravitational waves can merge them. So this is the dynamical explanation of the mergers. And there are some exotic explanations, such as this one, which is very exciting. So one possibility is that the dark matter in the universe is comprised of black holes. And if this is the case, then there was a paper which showed, right after the discovery, which showed that if 100% of the dark matter is made of 30 solar mass black holes, then you can calculate what is the expected rate of encounters and the rate of mergers between these black holes, and those matched the observations. So this was exciting. And by the way, there were previous electromagnetic searches for these types of objects. And so this idea is not new, that maybe the dark matter is made of black holes. But previous observations ruled out, or seem to have ruled out, the possibility that dark matter is made of black holes. Because if it was made of black holes, then you should see so-called microlensing events. So you should see, in some cases, these black holes should fly across the line of sight to a background source, electromagnetic source, and you can see the bending of the light waves as the object passes along the line of sight. These microlensing events should be much more abundant if there are many black holes in the dark matter, and it turns out that these types of observations can rule out black holes constituting dark matter if the black holes have masses of order 10 solar masses, which was believed to be the mass of the black holes at the time because of electromagnetic observations. But now it turns out that the black hole masses are larger. In that case, you need fewer of them to build up the dark matter halo. So you would not see these microlensing events. So that part of the space was not ruled out in the past, but no one thought that it was reasonable to expect such heavy black holes. But now it was predicted that maybe this explains the dark matter. But then there was another paper which claimed that, okay, if dark matter is made of black holes, then you should not see globular clusters at the centers of galaxies, near the centers of dwarf galaxies. The dwarf galaxies are these very low mass galaxies, which are predominantly made of dark matter. So they have much more dark matter than luminous matter, these dwarf galaxies. And you still see globular clusters in them. And these globular clusters should have been disrupted by these passing massive objects, these stellar mass black holes, if dark matter was made of these stellar mass black holes. So just because you see the globular clusters is an argument against the theory that black holes constitute dark matter. And then there was a newer paper by the same group. This one, which showed that actually there was an error in the initial calculation. It was an approximation. And actually, only 1% of the dark matter should be in black holes, and then you can already explain the observations. So black holes merge much more often than previously thought, and so you don't need all of the black holes to be, all of the dark matter to be in black holes to explain the observations. And in fact, there's a different group which looked at the possibility of primordial black holes. So if you form black holes in the early universe, how often do you merge them? And in that case, it turns out that it's sufficient to have 0.1% of all the dark matter to be in black holes to explain the observations, the high rates of mergers that we see. And so this is a possibility. And it's hard to rule out this possibility at the moment, so it remains a possible explanation. But the problem is the mass distribution is not really explained by these ideas. So why is it that you actually form these types of black holes and not, let's say, 1,000 times smaller mass black holes, for example? There's nothing special about this mass range. And so the summary is that there are different ideas. So there's the galactic field binaries, there's the dynamical channel, globular clusters, galactic nuclei, or the dark matter halos, but all of them have problems, as I will show. So there are arguments against all of these possibilities, and the bottom line is that there's no convincing single theory to explain the observations. I will come to the details in a moment. So first of all, for stellar evolution, so this is the general picture. You have two stars, one of them turns into a red giant, it explodes, forms a black hole, and then the other object turns into a red giant, maybe engulfs the black hole, and then you form another black hole, and then you merge them. The problem is the theory is not very well developed. So there are question marks in the different phases of this theory. And the most question marks are here. What happens when the black hole is inside the star? It's not clear. Does it go to the center? Or if it doesn't, what halts it from going right to the center? And how exactly does it go? So what happens to this remnant? Does it turn into a black hole and so on? The only part of the story which doesn't have question mark is the very end. When you have two black holes in orbit, you can calculate the general relativity. But so there are many unsolved problems here. And so the problem is there are three parameters in this theory that you can adjust to match the observation. So it's hard to rule it out. But one way to maybe rule it out is to ask if the theory matches the prediction. So the spins should be high in the case of binary evolution. So if you have two stars so close that they will merge as when they turn into gravitational black holes, if they're so close, then the tidal interaction between the stars should spin them up. And you should see highly spinning black holes when they merge. And the spins should be actually perpendicular to the orbital plane because so that's that natural configuration. And so if you see, you look at the electromagnetic observations, what you see is that there are three electromagnetic observations of stellar binaries, so stars with a black hole binary, where the black hole is massive. So these are progenitors of black hole binaries. There are three of them, and the spin of all three of them is close to 1. So it's almost maximally spinning. It's for one of them it's larger than 0.95, for the other is 0.92, and this is 0.84. So they are highly spinning. They should be aligned. This is exactly what is ruled out by the gravitational wave observations, which show that they are either not spinning or not in the direction that they should be spinning in. That's a problem. Okay, so what about dynamical environments? So this is an image of a globular cluster, so you can observe them very well. And it's a theoretically clean problem. So there are not so many question marks as previously. So this you can just simulate. You can just put it on a computer, put the stars, evolve them, and see what happens. The simulations show that the center of the cluster becomes denser and denser. You form binaries, and the binaries interact with stars, and they basically eject stars during these three-body interactions. And the cluster slowly evaporates. So it slowly loses stars, and eventually the cluster disperses altogether. So this is the prediction of these numerical simulations, that eventually these clusters disappear. So the only reason why we see the clusters is that there wasn't enough time yet for the clusters to disappear. And so you can examine these dynamical environments and theoretically, and there are different elements of this. So there are different dynamical processes. So there are triple scattering. This forms binaries. There are binary interactions with single stars, binary interactions with binaries. And it turns out that all of these types of interactions promote massive objects, the merger of massive objects. So it's more likely to form binaries if you have a massive object encountering other objects. And if you have a stellar mass binary and a massive object flies by, the massive object replaces. So if there's this chaotic interaction between the binary and this object, turns out that the outcome of this interaction is that the binary takes the place of the one of the low mass stars and ejects the star. So it basically replaces the star and sits in its place. So if you have a black hole to begin with, interacting with the stellar binary, it will just kick out one of the stars and become a member of the binary. And then another black hole can come by and kick out the other star, and this way you can form a black hole binary. And similarly, if you have binary interactions, that also leads to the formation of black hole binaries, and in particular, the most massive black holes will tend to form binaries more easily. And there's also dynamical friction, so the heavy objects will sink to the center of the globular cluster and have many more interactions. So the prediction of these types of models is that more massive black holes will merge more often. And so this is consistent with the observations. So this is a simulation we have done, or two different types of simulations with some postdocs in my group, and which showed that the probability of merger, it scales with the fourth power of mass. So indeed, higher mass objects merge more easily in these systems, in these numerical simulations. And you can also predict the distribution of total mass versus mass ratio in these systems. And this is a contour diagram showing the merger rates for different masses and mass ratios. And this shows that most likely is the merger of comparable mass objects. It is less likely to have very large differences between the masses of the merging objects. And there's also a population of these objects, which are mergers of the merger remnants. So you can have a merger remnant where the remnant stays in the cluster and merge again with another object. And these will be found here. The simulations show that this is 7%. In a globular cluster, which means that if we see this population being 7% of the rest of the population, then it confirms the theory. But this is yet to be seen. So there's now evidence of these hierarchical mergers. So there are some black holes, 4 or 5 of them, some of these mergers, which are in the range, which are in this range above 50 solar masses. So these black holes cannot form through just simple stellar evolution. It turns out if you have a massive star, you can have a star of 150 solar masses, but it will not form a black hole of 80 solar masses because it loses most of its mass before it turns into a black hole. So these are theoretical models of stellar evolution, which cannot explain these objects. So the idea is that these objects may be the result of mergers, of black hole mergers. And you can ask, well, what is their relative likelihood? But the problem is there are too few observations at the moment. So, so at the moment, it is constrained to be between 5% to 0.05%. So maybe not quite enough for the dynamical channel, which would predict 10% or 7%. And what about the spins? So in the case of the dynamical channel, the spins can be random because you form the binaries in random ways. You don't form them when the stars are very close. And so if there's an isotropic distribution of spins, on average, this component that is observed could be centered around 0. So this is in principle consistent with having 0 spin in projection. So what about the rates? So there's a problem with the rates. So you can estimate the rate of mergers in globular clusters, and there you can make very simple arguments. Just assume that for an upper limit, that every black hole in a globular cluster merges. And you know how many black holes you have in globular clusters because you know how many stars you have. You just see the stars. And you can infer that the massive stars should have turned into black holes by now. And so if you know what the mass distributions of the stars is, then you can just infer the number of black holes in a globular cluster. So the prediction is that general understanding is that 0.3% of the stars turn into black holes. This is very general. And if you know how many stars you have, you know how many black holes you have. And if all of them merge, then you get the rate of mergers because you know how many globular clusters you have in the universe. And this rate of mergers, this upper limit, ends up being 40 gigaparsec cube per year. And remember that the observed rate was between 15 and 39 per gigaparsec cube per year. So you need almost all of them to merge, which is quite high. In simulations, you find that only 20% of them form binaries and only half of the binaries merge. So basically 10% of this number, something like 4, actual calculations, simulations show 6 per gigaparsec cube per year. But it's much less than the observed rate. So there's a very high rate of mergers inconsistent with the prediction. So this is the summary. So we're back at this conclusion. There are no convincing single theory to explain all of the observations. It may happen that you have a combination of these different channels, but in a way that's already surprising. A priori, you could have, if you have so different types of astrophysical events, you could have expected one of the events to dominate. How unlikely is it that they all produce exactly the same rate, which then add up to the observed distribution? And so now I will show some new ideas in the remaining of the time to explain the mergers. These are some papers we put out with some students and postdocs in the past years. So one idea is disrupted globular clusters. I will show you. Since the globular clusters disperse, there were many more globular clusters originally than we see today, and maybe this explains the high rate of mergers. The other interesting idea is that the black holes are not distributed like the stars in these systems, but they form a disk, and then they merge much more often. And also mergers can happen around supermassive black holes. So this is what my title of the talk was about. And so first, so let me show you in a little bit more detail what I mean. So first about disrupted globular clusters. So the prediction is that globular clusters were much more numerous in the past than today because they just disperse by themselves. So they form binaries, the binaries eject stars, and so they lose mass and eventually disappear. And so you know how many globular clusters you see at the moment, so you can infer how many you should have had in the beginning. Turns out you needed to have 8,000 globular clusters to explain the 100 globular clusters that we see today. So there are many more in the past. And those globular clusters could have formed the merging black holes that happen to merge today. So this is the idea. And so here there are previous papers. So this idea is not new. This was known from the 70s. So maybe this is how the globular clusters evolved in the galaxy. And you see that if you start from this type of distribution, so this is the number density as a function of mass. So these globular clusters have masses between 1,000, 10 to the 3 solar masses, up to 1,000,000 solar masses, 10 to the 6 solar masses. And at the moment, this is the distribution that we see for these globular cluster masses. And in the past, this is what you should have had to produce this by now. And so you can see that they are 10 to the 4. So this is the 8,000 globular clusters. And you can also look at the radial distribution of these globular clusters. And if you start from this type of this initial distribution, you find this type of distribution which matches the observations. So so if you make these calculations, so if you evolve these globular clusters on the computer, maybe I should turn this camera so you can see me. So if you carry out these calculations and you see how many globular clusters how the globular clusters evolve in the galaxy and how often they produce mergers, you can get the rate as a function of redshift, as a function of distance in the universe, which will be higher than the rate without this effect. But it turns out it only increases the rates by a factor of 3. So it's not clear if this actually explains the observations. So it turns out that these globular clusters, the low mass globular clusters, do not contribute much to the merger. It's only the high mass globular clusters that contribute, and there are relatively few of them. So this idea is maybe useful to increase the numbers by some amount, but maybe not enough. And but in the future, you can look at the redshift distribution of the sources. At the moment, you only see the nearby sources, basically. And if you see the redshift distribution corresponding to the formation of globular clusters, then maybe it will be an argument in favor of this type of theory. And you can also see the mass distribution, look at the mass distribution, and compare that with the observations. So the other idea is these disks of black holes. So this is really interesting that it turns out that the black holes, which are not seen in globular clusters, should reside in a disk and not like the stars. And this is because there's this gravitational interaction between these objects, and these objects, there are these long-standing gravitational torques that tend to align the orbits of these objects if they are more massive. So this is a process called resonance relaxation, and which implies that the massive objects form disks and low mass objects become isotropic in these systems. And black holes are more massive than stars, and so they should form disks. So this is a theoretical prediction. There's no observational evidence so far, but it's a theoretical prediction that explains the expected distribution of black holes in these systems. And if you shove all these black holes in this very small region, then you will merge them much more easily. So maybe this is why we see so many black hole mergers in the universe. And finally, black holes can merge in active galactic nuclei. So this is really interesting. If you have a supermassive black hole, it shines very brightly if there's a gas cloud around the supermassive black hole. And this gas cloud can act to collect all these stellar mass black holes and to merge them, as I will show. So the idea is that you have a supermassive black hole, so this is a toy model, a gas disk, and a population of stars and black holes around the supermassive black hole. There's a high density of them, as I showed you earlier. And so as they orbit around the supermassive black hole, these objects, they inevitably cross the accretion disk, the gas disk. And when they cross the disk, they lose momentum. So they interact with the disk. And ultimately, these orbits align with the disk, a fraction of these orbits. And this alignment is relatively fast. You can calculate in 10 million years, these stars and black holes should align with the gas disk. And then they quickly merge due to dynamical friction on the gas. So the gas, if these black holes are moving through gas, then they lose energy because of, waves they excite in the gas disk. And so the separation shrinks inevitably if you're in a gas environment, which doesn't happen if you're in vacuum. And so gas can help you to shrink the orbits, and ultimately gravitational waves can merge the orbits. And this process is also very fast. You know what is the density of gas in this region. And so you can calculate that in 1 million years, the black holes should merge. But this phase of the AGN phase, so when gas is around the supermassive black hole, doesn't last too much longer. So it is believed that in 10 million years, the gas cloud is absorbed by the black hole. So it disappears after 10 million years. So the question is if that's enough time for the black holes to actually merge. But if they merge, they can produce not only gravitational waves, but maybe electromagnetic radiation, because here the objects merge not in in vacuum, but in gas. So this is really interesting because you can observe not only the gravitational waves but also electromagnetic waves at the same time. There was actually one observation where there was an AGN flare 34 days after the LIGO event from the same region. And so this is a possibility that maybe this happened once at least. It is unclear if you would see the electromagnetic waves, even if they exist, because it could be very faint. So these systems are far away, and from stellar mass sources, the observations may not be bright enough to observe. Okay. So, so to investigate this in more detail, what kind of objects you expect in this channel, you can run numerical simulations. You can construct these different types of simulations, but you need to take into account the large variety of effects that play a role in these systems. So there are these binary single interactions, as in globular clusters. So you have a binary interacting with single objects. You have triple interactions, which form binaries. The disk captures the objects through the process I showed you earlier. And you can form, in this case, you can form binaries in gas much more easily than in vacuum, because the objects are going through gas, they lose energy. And so even if you have two objects come close, you can form a binary that way. And ultimately, if you have a binary embedded in the gas, then you can simulate what happens with them and how often they merge and what happens. So we tried to do all these calculations, and this is an example of a numerical simulation. This is run by Conor Rowan at Oxford in my group. And so here we're simulating a ring of gas to save some space. We're not simulating the distant regions of the accretion disk. And we put in two black holes in the disk and see what happens. And so as they orbit and they are at different radii, they ultimately approach each other. And now we just zoom in to see it more closely what happens. And so here we're showing the density. So you can see there are these high density regions due to the black holes in the gas disk. We're just changing now the color of the simulation to highlight more the effect. And so what happens is that the black holes come close ultimately, and they form a circumbinary disk. So they orbit around each other very rapidly here. And there's a gas disk here and a stream coming around, trailing and leaving this circumbinary disk. So the simulations show that you can form a binary just by this close encounter in gas. And then the gas can help the binary to merge. And so this is how it looks like, how the binary, this is zoom in, a high resolution zoom in on the two black holes orbiting, approaching each other in this accretion disk as they form a very close binary. Yeah, the simulation takes a while. In the end, they form a closed binary. And so this is how it looks like in the end, in the simulation. But what you can see is that there are these streams where there are these density wakes excited by the binary components, which take away angular momentum from the binary, and they can help the binary to merge. So here's, well, you can calculate lots of things. What happens to the orbital radius of each object of the binaries in the galaxy, and how the binary separation changes with time, and what happens with their velocities, what happens with their spins and the spin directions. You can simulate this. And so it turns out that there are episodes of these binary single interactions in these systems when the binary is kicked out from, so the binary is first embedded in the disk, they form in the disk, and you have a third object coming from outside, from the cluster, and they interact with the binary. And this interaction typically kicks out the binary from the disk. and then it's outside of the disk, but then it settles back into the disk ultimately. So each time it crosses the disk, it will lose angular momentum and ultimately settle back into the disk. But then there could be another episode when there's another binary single interaction, it kicks out the binary and so on. And in each case, you can calculate what happens with the spins. And during these encounters, the spin orientation is randomized. The binary orientation is randomized, the spins remain the same, but the binary inclination becomes uncorrelated with the spin of the binary. And so you can calculate what happens in the simulation from some initial condition to later times as a function of, so what is the binary separation and what is the distance from the supermassive black hole? So where are the mergers? Turns out that the binaries clump together at some particular radius in the accretion disk at 0.01 parsecs, and they ultimately form binaries and merge there. And so let me just jump over this. So this is, turns out that you will detect gravitational waves, not only with LIGO, but also with LISA in the future. So if this is the most important channel, you will see a lot of events also for LISA. So for the space instrument, gravitational wave instrument, at lower frequencies, you will see lots of these sources, which happen to be at these types of separations from the supermassive black hole. And so then you can ask, can you explain the mass distribution? Can you explain the spin distribution with this type of model? So you can also see what is the mass distribution in the simulation and the spin distribution. And it turns out that the mass distribution extends to high masses because you merge the objects so easily that the merger remnants can merge again with newer and newer objects. So you have these hierarchical mergers more easily in these types of systems. And so these systems will be sometimes more massive, and they will be highly spinning because gas tends to spin up the black holes. So they will be highly spinning, but the spin direction will not be aligned with the orbit because the orbit is randomized by these binary single interactions. So you should see high spins, but not in an aligned configuration. So this is still possible compared to the observations. And there's a prediction that there's a perpendicular component of the spin, which is only measured for a few cases. In this one case, for example, this should be large, this perpendicular component of the spin. And so this is consistent with this type of observation. The rates are very uncertain, so we basically don't know. We attempted to estimate the rates of the mergers in the simulations, but they just span such a large range that you cannot really use it to confirm or rule out this type of possibility, even representing 100% of the mergers. You can look at the spin distributions. They also seem to be fairly consistent with the observations. And another prediction is that we should see eccentric sources. So most of the sources that LIGO has seen to date were circular mergers, but in principle, you can have eccentric orbits, highly eccentric orbits, which should then result in a merger. And for these systems, you can simulate them, and it turns out that a few percent of them form these eccentric mergers. And there's one observation at the moment, which was inferred to be highly eccentric. So maybe this was an example of this type of merger happening around the supermassive black hole. But different models have different predictions for the fraction of these mergers. So it's not clear if it should be exactly a few percent or maybe even higher in these models. Okay, so the conclusion is that the black holes merge frequently in active galactic nuclei. And there are some distinguishing features that can be used to identify this type of population in the merging population. And so one of these is that there are repeated mergers. So the mass distribution is higher, higher masses are more common. And black holes should have a spin around 0.7. So it turns out if black holes merge, they will have this type of spin. And there should be a statistical correlation between the spins and the mass. The scatter of the spins should be large at high masses. And the black holes should be spinning and aligned with each other, but not with the orbital plane. And this is something that can be checked in future observations. So this is the summary. So I think I hope I have convinced you that this is a very exciting field at the moment. So now 90 black-hole mergers have been detected by LIGO and VIRGO, and the new observations are just starting in May. So the LIGO and VIRGO instruments have been improved, upgraded during the past couple of years, and now it will be turned on. The new very high sensitivity instrument will be turned on in May, and we might see a merger every couple of days from that point. And so we might be able to distinguish between these astrophysical merger pathways. And so we can use the distributions of these parameters to test the theories. And gravitational waves probe the astrophysical systems in new ways. So we can maybe look at globular cluster evolution with gravitational waves. So as globular clusters evolve in time and evolve with galaxies, they will produce different rates of mergers at different times. So if you measure the rate of mergers versus time, then maybe you will learn something about galaxy evolution. You might also learn about active galactic nuclei. So you can use these systems to test models of gas interactions with black holes. So there's a very bright future for gravitational astronomy. There are new instruments coming online. So there's the Japanese instrument becoming better and better. And there's also, so the Japanese instrument has a completely different technology, and in principle, it should reach the same sensitivity as LIGO, or maybe even better. And there's also a new type of LIGO instrument being planned to being installed in India. So that's another, this is an ongoing development. And there are plans for further upgrades. So there's going to be LIGO Plus, the Cosmic Explorer, and the Einstein Telescope, and maybe LISA in the future. So I will, and here just show this horizon distance for future Earth-based instruments. So as you can see, at the moment we are at advanced LIGO. So this is the current sensitivity. So this is the redshift range we can reach. So up to redshift 1 maybe, but typically only much less at these masses. If you have very high mass black holes, you can see them further, but only up to redshift of 2, let's say. But in the future, when you will have Cosmic Explorer and maybe Einstein Telescope, then you can go all the way to the dawn of structure formation to very distant regions of the universe. Thank you very much.
Very interesting talk. Thanks so much. One of the questions would involve that system that you mentioned that featured an AGN flare a couple of days, a week afterwards.
Yes.
And I was kind of wondering how well you can localize the sources on the sky.
Yes.
And how easy it is to say something about the proximity of an AGN.
Yeah, that's a very good question, and I should have emphasized that the localization with gravitational waves is very poor. So at the moment, typically they cannot be localized to better than a few degrees on the sky, which in that region there are thousands of AGN. So it's not clear. It's not like you know exactly where the sources are happening, where the sources are being produced. And so in that region, you have a large sample of AGN. And the AGN are also variable. So as gas is flowing around the supermassive black holes, it produces luminous emission, but this emission is typically varies. So you might think that maybe it's just by chance that it became so bright at the time. But at the same time, on the other hand, these variations are relatively slow. So the typical timescale of the variations is on the timescale of months to years, like 6 months to few years. So on that timescale, the AGNs can vary a lot in luminosity. But in this case, there was a very rapid brightening, which is very unusual. And it was consistent with that region, but it's unclear if this was triggered by the black holes. So I think it's more research is required to make firm predictions on what to expect to see, and then test those theories observationally. But once you will have many more instruments, then it will be possible to localize the mergers much more accurately. In particular with LISA, you will be able to localize the sources much more accurately, but still probably not enough to isolate galaxies. Maybe enough to isolate AGN, which are rarer in general than galaxies.